All right, welcome to day 5. Homework is day 5 textbook problems. So we'll scroll down to check your homework answers. Now, for each of these, when it just says diverges, converges, you need to have the justification, obviously, with them too. We're going to pause for 3 minutes for you to check these answers, and then we'll go through slide by slide of the worked out solutions. All right, so our first one, we had fifth root of p in the denominator, so that means your p-value is 1/5. Anytime p is greater than 0 but less than or equal to 1, that's a diverging p-series. In 15, that's the same as having the series, sum n equals 1 to infinity of 1 over n to the 1/2. So that's a p-series where p is equal to 1/2. So same reason as in 13 of why it diverges. P is greater than 0, less than or equal to 1. So divergent p-series. Now you can't just say p is less than or equal to 1. You got to say p is greater than 0, but less than or equal to 1. In 17, this is 2 to the first times 2 to the 1/2. So all of these are actually raised to the 3/2. So this is a p-series where p is greater than 1, so it converges. And then the last one, number 19, the exponent in the denominator there raised to the 1.04, that p is greater than 1, so that would be a converging p-series. All right, so first converges, diverges. In 21, because we're raised to the 3/4, we would have diverges because p is greater than 0, less than or equal to 1. In 22, we have p is equal to 1. So that's again diverges because p is greater than 0, less than or equal to 1. That's also the same as our harmonic with a 2 just pulled out front. And then in 23, we've got that very similar to what we saw in one of the problems on the last side. N to the first times n to the half. We really have n to the 3/2. So that's p is greater than 1, so that's converges. And then 24, p is also greater than 1, so that's converges. From there, you can just sub in a couple n values and see what's going on to decide which ones we had. So 21 matches with choice A, 22 with D, 23 with B, and 24 with C. A big idea is if you're ever unsure about a series, sub in the first couple values, and that can give you just a bit of a sense of what's happening with the series. For 38, we wanted to do the fourth partial sum, so just do in your calculator summation from 1 to 4, and we either get the fraction form or the decimal form there. Doing our integral remainder, we do our integral from 4 to infinity of 1 over x to the 5th dx. We switch that to our limit for our improper integrals, do our antiderivative and sub in, and you get 1 over 1024. So what this is really showing is s, our exact infinite sum, minus the partial sum, is 1 over 1024. Or in other words, our partial sum is missing at most 1 over 1024 of the infinite sum. All right, the next one, we had our series here, and we wanted to know how far did we need to go out in order to ensure we are within 0.001. So in 38, we had a 4 here. In this one, we don't know that thing, so I'm calling it capital N. We're going to go to infinity again, which I went right ahead and made that a b. Do your antiderivative and sub in. When b goes to 0, or when b goes to infinity, the first term goes to 0, so we get this. You can multiply the square root of n over to the right. It does not switch the direction of your inequality because n was going to be some positive integer. The 0.001, if you divide that over, that's like multiplying by 1,000, so we get 2,000 on the left. And then when you get n by itself, we would need n to be greater than or equal to 4 million. So you'd have to go out 4 million terms in order to ensure that you're within 0.001 of the infinite sum. 57, our absolute value of r is less than 1, so geometric, we're converging. 58, absolute value of r is greater than or equal to 1, so it's geometric and we are diverging. And 59, you might be able to just see it by writing out a couple terms, but those numbers are not getting smaller. So therefore, limit as n goes to infinity of our individual terms an, that is not approaching 0. So then by the nth term test, that automatically diverges. Nth term test can only be used to show divergence. If you find that the individual terms are going to 0, that's great. We would still need to determine whether or not it is going to converge or diverge, because some things that the individual terms go to 0 are diverging, some are converging. And just think about our p series. We know there is that dividing line of the exponent. If you're greater than 1 or less than or equal to 1 would determine that divergence or convergence. Now, the way to think through this algebraically is over on the left there. When n goes to infinity, that plus 1 is going to be inconsequential. So think of it as n over square root of n squared, which would give us absolute value of n. When n goes to a positive infinity, that's really just n over n, which will end up going to 1. So that shows there that the individual terms aren't going to 0, but you don't necessarily need that. If you just look at a couple of the terms, you could figure that out as well. So to do integral test, we need to be positive, and when we combine our terms, notice eventually these are all positive. They are decreasing, and the function would be continuous from 1 on. So we can do integral test, starting at 1 and going on forever to the infinity, which will eventually make that a b. When we do our improper integral, we eventually get that it is 3 halves. So therefore, our series converges. Now keep in mind, this doesn't show that it converges to 3 halves. Just the fact that it's a finite number means the series converges. Another way we could show this converges is you could split it into separate series. Those individually are p series that converge because p is greater than or equal to 1, so their difference would also be convergent. And at the end here, I kind of added in, but we should say it converges by the integral test. For 61, as n goes to infinity, that's our 1 plus a tiny raised to a huge, so that's e. Because our individual terms are going to e and not going to 0, automatically that diverges by the nth term test. And natural log as n goes to infinity, that keeps growing forever. So because our individual terms are not approaching 0 when n goes to infinity, automatically we are diverging by the nth term test. All right, so we want to be in day 5 in our notes packet. And we're going to look at 2 tests today, the direct comparison test and the limit comparison test. So first, an example to highlight the direct comparison test. Let's say we have Joachim, and Joachim, based on his height, we would call him a giant. And based on her height, Mitzi, we would classify as a little person. If Wendell's taller than Joachim, let's jump down here and see what could we conclude about Wendell. Well, if Joachim is a giant, and we know Wendell is taller than Joachim, then we could say that Wendell would also be a giant. Because anyone taller than Joachim should have that same title. If Preston is shorter than Mitzi, let's jump down to the bottom here again. What can we conclude about Preston? Well, if Mitzi, based on her height, is classified as a little person, then we could say that Preston would also be a little person. So if you think of it kind of like a number line, if Joachim is here. Anything bigger than Joachim should be a giant. Well, Wendell was bigger, so Wendell was also a giant. If we think of Mitzi being here, and anything less than Mitzi is a little person, well, if Preston is shorter than Mitzi, Preston is within that span that we would consider a little person. Now the third one down, Mrs. Kushner is shorter than Joachim. So Mrs. Kushner would be somewhere in here. We don't know where though. So what can we conclude about Mrs. Kushner? Nothing. Amanda is taller than Mitzi. So we know Amanda is somewhere in here. What can we conclude about Amanda? Nothing. So essentially what this says, if we know someone's tall, anyone who's even taller than them would be tall. If we know someone's short, anyone shorter than them would also be considered short. But if it's on the other direction, where they're not on the polar ends of things, we can't make any conclusion. So here's a visual of the same idea. If we consider Will Ferrell to be tall, anyone bigger than him would also be considered tall. If we consider, say, Tom Cruise to be short, anyone shorter than Tom Cruise would also be short. But if we know someone is bigger than Tom Cruise, that alone does not allow us to classify them at all. So those are just two examples to represent the direct comparison test. So let's think of it in terms of series now. Let's say we've got two series where the terms are greater than or equal to 0. The terms of the first sequence we'll call A are always less than or equal to the terms of the second sequence B. Now it says for all n greater than m. So basically that means eventually we need all of A's terms to be less than their counterpart in B. Let's say that B converges. And B we know is always going to be larger. If B converges, anything smaller than B should also converge. So if you're shorter than a little person, you're also a little person. Oops, I guess it's below here. So the reverse would be, let's say we knew the small one diverged. If anything diverges, anything bigger than it will also diverge. So if the sum of AN diverges, then the sum of BN would have to also diverge. So if a series is converging, anything we know smaller than it will also converge. And if a series is diverging, anything larger than it will also diverge. And that's the idea of the direct comparison test. So if we go over to the next page, we want to know, our question pretty much always in this unit is this series going to converge or diverge? We're unsure at this point, so what we do is we pick an easy series that we can use our tests that we've already seen in this unit. So what we're going to say is we're going to compare it. You always write compare to, and then write what your nice series is. We're going to compare this to n equals 1 to infinity, and we're going to do 1 over 3 to the n. Similar to the one we have, but that plus 2, by knocking it off, it'll make it easier to work with. Because we can rewrite this as sum n equals 1 to infinity. Well, 1 raised to any power is 1. So we can think of this as 1/3 all raised to the n. Because 1 to the n would be 1, 3 to the n is 3 to the n, so that would match that series we have there. Well, hopefully this is something we recognize now from the past couple days in class. We could say that this is geometric with absolute value of r is less than 1, so it converges. Well, let's compare our terms in our nice series compared to our original series. If we take 1 over 3 to the n plus 2, and if we take 1 over 3 to the n. The left-hand one, the denominator is always larger. If you are dividing by bigger things, that will always make your value of the fraction smaller. So therefore, we know that the 1 over 3 to the n plus 2 is always going to be smaller than 1 over 3 to the n. Well, let's think about this. We know the 1 over 3 to the n is going to converge. That means everything smaller than it will also converge. So we've just shown it's smaller. We showed the nice one converge. So all we got to say now is, so by the direct comparison test, our original one, sum of n equals 1 to infinity of 1 over 3 to the n plus 2, converges. So you compare it to a nice series that we can quickly determine converges or diverges. We relate it to either being greater than or equal to or less than or equal to that nice series. And then we see if we can make a conclusion of if something's diverging, everything bigger than it will diverge. If something's converging, everything smaller than it will converge. Now down on the bottom we have a visual. So the bottom one is our original, the top is our nice one. We knew that our original was always going to be less than or equal to our nice one, and we see that here. The top one there is converging, that was our nice one, so essentially the bottom one will also converge because it's going to stay less than or equal to it. So let's try another one. Does this series below converge or diverge? Well, let's compare it to something nice. So let's compare it to sum n equals 1 to infinity of 1 over n cubed. Now I should say this is our day on direct comparison test and limit comparison test, but usually the first thing you would think about is if nth term test could apply, because that's a pretty quick one. And as the terms go to infinity in this original series, the denominator's going to get huge, so the terms will go to 0. So it's not going to diverge by nth term test, but that's usually a first one you would think of the ones we've seen so far. All right, so we're going to compare it to this nice one. We want to recognize this as a P series. So we'll say P series with RP being greater than 1, so it converges. Now we're going to compare the two. We've got our original 1 over n cubed plus 1, and we've got 1 over n cubed. Same idea as before. When you add more to the denominator, you're dividing by a bigger thing. When you divide by a bigger thing, it makes the value of your fraction smaller. So we would have our original as less than or equal to the 1 over n cubed. Now I say less than or equal to because that's in the original um, definition of a of n being less than or equal to b of n. Most of the ones we see, they'll be strictly less than. So if you can think through and based on the values of n you're subbing in, if you know it's going to be just less than, it's okay to just do that. If you want to be safe, you can just say less than or equal to, because that's all the threshold we need to be able to use this. So 1 over n cubed converges. That means everything smaller than it will converge also. Well, we just showed our original is smaller than it. So we can say, so our original converges by the direct comparison test. All right, let's look at another one. We want to know if this series converges or diverges. So let's pick something nice. Hopefully by this point, you're comfortable picking out that 1 over square root of n would be a nice one. This is really 1 over n to the 1/2. This is a p series where p is greater than 0 but less than or equal to 1. So it diverges. Let's compare our two things. Our original 1 over square root of n plus 2 and 1 over square root of n. When you add something to the bottom, you're dividing by a bigger thing. When you divide by a bigger thing, it makes the value of the fraction be smaller. So our inequality would go that way. If our nice one is diverging, it means everything bigger than it will also diverge. Well, our original is not bigger than it. So for this case, direct comparison test does not apply. So what this tells us is we need another test. Okay, and there's just a visual of the one that we just looked at. But let's go down to the bottom to the limit comparison test. So if our individual series are greater than 0, the terms are greater than 0, and if we do the limit as n approaches infinity of the ratio of our two series, if that equals some finite positive number, then both series will do the same thing. Either both converge or both diverge. Now, it doesn't matter which one you put in the numerator and which denominator, because let's say this L gave you 2 when you did A of n divided by B of n. If you flip them, you would just get a half, and that's still a positive finite number. So limit comparison test would still apply. So it doesn't matter which order you do it in. Now, I'm going to put this right above, in the space above where it says limit comparison test on yours. But let's show that we could use limit comparison test in the one from the other page. So our individual terms we had, again, this is from the bottom of the previous page. You had 1 over square root of n plus 2. That is always greater than 0 when we sub in n values of 1, 2, 3, 4, and so on. Same thing with our nice one that we were doing. That was already all set. So to do limit comparison test, the full thing we would write, we would still say compared to this sum n equals 1 to infinity, 1 over square root of n, which was a p series with p greater than 0, less than or equal to 1, so diverges. We thought about direct comparison. We saw that didn't work. So we're going to try limit comparison test, where we do limit as n approaches infinity. And we're going to divide these two here. And I wrote a 2 here. That's supposed to be an n. Sorry about that. That should be square root of n. Well, we're dividing fractions, so we're really doing a keep change flip. I'm going to do the top one there divided by the bottom one. So when I do a keep change flip, eventually it's going to end up as this. Oops, not the 1. So as n goes to infinity, notice I've got ratio of the leading coefficients is what I'd want to do because our degrees are the same. They're both raised to a half. So this would end up approaching 1, which is greater than 0, which means our limit comparison test would apply. So we would just say that the sum of n equals 1 to infinity of 1 over square root of n plus 2 diverges by limit comparison test. And again, this was from the one from the previous page, just to show you we ran into a roadblock with direct comparison test. So now we could do it with limit comparison test. Well, let's try another one. This is on the bottom of that page now where we just talked about limit comparison. So we want to see if this converges or diverges. We should think through our nth term test. As n goes to infinity, this fraction is going to get smaller and smaller. So nth term test would not lead us to a diverge. So therefore, we'd want to try something else. Let's try and compare it to something. So we've got 1 over n. These are both always going to be positive when the n's are positive integers. So we're in good shape there. And let's now do our limit as n approaches infinity. And if we divide the two, I'm going to do the original divided by this one. And actually, pause 1 second. Before we do the limit comparison, let's just say what we know about 1 over n. You can say one of two things. You could say it diverges since it is harmonic. Or you can say it diverges since p series with p greater than 0, less than or equal to 1, because this is really a 1 here. Now, we saw on our p series day that when p was 1, that it diverged, and that's a special series called the harmonic series that's really popular. So because of that, that's a common one that's known. If you see it, you can just say it diverges since it's harmonic. Or if you want to write it as the p series way, either one of those is fine. So we should probably write that first before we get into our comparison test. Now, if we're going to diverge, if we were going to do direct comparison, we would need the thing to be bigger, but our one in the original would be smaller because we got extra stuff added on. So that would lead us to not use direct comparison. So in our new one, limit comparison, we're going to do limit as n approaches infinity. I'm going to divide my two fractions, so a keep change flip would make n end up on top, 2n plus 3 on bottom. The highest degree is the same in both. They both have 1s in the exponent. So we'll do ratio of leading coefficients. So we get a half, which is greater than 0. It's a positive finite constant. So we are ready to do our conclusion. We can say that our sum n equals 1 to infinity of 1 over 2n plus 3 diverges by limit comparison test. If when you divide them, you do the limit as n goes to infinity, the limit equals a positive finite constant. The series that's not nice will do the same thing as the nice series. We showed the nice series diverged, so therefore our one we are actually trying to investigate will also diverge. Next one, we're going to compare this with a nice series of 1 over n squared. That's a p series. Where p is greater than 1, so converges. If we think direct comparison test, we would need stuff to always be smaller than this nice series. And a problem with that is, for example, when n equals 2. In n equals 2, this original will be a third, but this one will be a fourth. So the original series is not always smaller than the nice series, so that means we can't do the direct comparison test. So we'll have to do limit comparison test here. So we're going to do limit as n approaches infinity. If we divide the two, I'm going to do the top divided by the bottom. Keep change flip will eventually give me n squared over a half n squared plus 1. Same degree, so ratio of the leading coefficients will give me 1 over a half. Keep change flip for that will give me 2. 2 is a positive finite constant. So that means our limit comparison test checked out. So we can say that our original series, n equals 1 to infinity of 1 over 1 half n squared plus 1, will converge by limit comparison test. If you don't get a positive finite constant, then you can't use limit comparison test. We'd have to use something else. All right, one last one for this video. How are we deciding this thing to compare to? Well, notice in every case, to get a positive finite constant, we wanted to end up with the same degree as our largest power. Here we had the squared same degree. In this one, we had n's as the same degree. This one, we had n to the 1 half. So we want the same degree both top and bottom. So let's look at our highest degrees. Here you have a 1 half. Here you have a 2. So we would want to compare this so that when we divide, we end up making them equal. So this basically needs 3 halves more for it to be equal. Well, for it to end up on top, we would want to divide by 1 over n raised to the 3 halves. So we're going to compare this to, I guess I already have compare written there, so I don't have to write compare. N equals 1 to infinity, 1 over n to the 3 halves. So basically, it's the gap between the two, so that when you divide them, you will have the same power as the highest degree, both numerator and denominator. Let's say what this one does. It's a P series where P is greater than 1, so it converges. Let's do our limit comparison test. Now when I divide by 1 over n to the 3 halves, I'm really going to multiply by n to the 3 halves. That n to the 3 halves will have to distribute to both terms in the numerator though, so we'll get 4n squared minus n to the 3 halves all over our original denominator. As n goes to infinity, we just care about those terms with the highest power, same degree, so ratio of the leading coefficients would give us 4, which is a positive finite constant, so we're in good shape. So we're ready to write our conclusion now. We can say that the limit, sorry, not limit, but the sum, n equals 1 to infinity of 4 square root of n minus 1 over n squared plus 2 square root of n converges by the limit comparison test. And that's it for this video. Have a great rest of your day.